Hey everyone, I'm Nick, and in this episode of C++ Crash Course, we're going to be talking about Google Benchmark and how we can use Google Benchmark to automatically generate some micro benchmarks in order to test out snippets of our code to better understand their performance. So let's go ahead and get started. Now, if you want to look at how to download and how to get started with Google Benchmark, you can just go to Google's repository for it and just Google Google Benchmark. Right, and it has an install guide here, and it also has some very basic benchmark examples in here as well. Right, so today we're going to be looking at one that's a little bit more interesting, which is a cache benchmark. So let's go ahead and get started with that. All right, so the first thing that we want to do is understand how do we write a benchmark using Google Benchmark. So the first thing we need to do is include a header, right, which is this benchmark slash benchmark.h, right? So this comes from Google Benchmark. The next thing we do is we define a function, right? The function is going to serve as our benchmark, right? So we'll have this static void cache bench, right? So this will be our benchmark, and then we'll need to pass in this benchmark state by reference. Then in here, right? So this reference that we're passing in, or this state, this will contain any inputs that we're going to be passing to our benchmark. So in this case, we're going to be passing a certain number of bytes in, right? And these bytes is what we're going to use as our working set size for our test. Right, so we're going to be exploring, the memory hierarchy of our system using this benchmark. So we're going to divide this by 2 and turn it into integers because what we're basically going to do is have one vector of just values, right? So these will be just some random numbers between int min and int max, and then over here we're going to compute one of indices, right? And this one of indices, it will just be random positions within the range of that other vector. So we're basically going to use one of these vectors to randomly access the other vector. Now, what use case scenario does this kind of, is this typical of? So say something like a map in C++, right? There's a level of indirection between getting from how you index it to the actual values on the other side, right? So in that level of indirection, it can be, what you're accessing could be sprayed across the memory system, right? So you can use a map, or just as some more clarity, right, you can think of it as a vector of random indices accessing random parts of another vector. Right, so here we'll go ahead and push all these back, and then we'll have this while loop here. And in this while loop, what we'll end up doing is just start accessing and accessing and accessing that vector of values, accumulating a sum, right? And then just to make sure that we don't optimize out sum, we'll use this do not optimize sum. So then we'll add a couple things at the very bottom. Here we'll add the set bytes processed. So this is going to be s iterations times long bytes. So we want to figure out how much data are we working with here, or are we transferring around. And then we also want to insert a custom label here. So this will just get printed out for us. And we want to figure out how much, like in kilobytes, we've transferred around. So that will just be bytes divided by 1024. Now, in order to actually run our benchmark, we have to first register it. So we register the benchmark using this function benchmark, right? And we give it the name. So in this case, we called our benchmark cache bench. So we give it cache bench. Then if we want to put an input, say like a range of numbers we want as an input, we can use this dense range. And here we want to say test 2 to the 13 to 2 to the 26. So then the next thing is we can say, report aggregates only, right, and set this to true. Now this will just help us to limit our output. Then of course we have to, every C++ program needs a main function, right? So we're not going to define our own main function. We can just call this benchmark main. So you can think of that as basically our main function, right? And so that's it. So we're able to create a benchmark just like that and not have to worry about, anything else, right? So let's go ahead and or any of the other boilerplate stuff. So let's go ahead and compile this. So to compile this, right, and let's go ahead and look. So this is the simple RNG function. All it's doing is going to push back a random number, mod end plus begin, right? So begin's giving the offset, right? Count times. So let's go ahead and compile this. So to compile, we'll just use g++ cache bench. Now we need to set the standard equal to C++11. Because we're using things like auto types and we're using those kind of for each loop things. So then we'll go ahead and we have to link against a couple things. So we have to link against lib benchmark, Now libbenchmark is going to be from that Google benchmark repository that we, if you go through the instructions, you'll make everything and you'll install it. The next thing is lpthread, and we'll set our compiler optimizations to 3. Then the next thing, right, we'll just give it a name, right? So we'll say -o and then say cache bench, right? And that's all we need to do to compile it. So let's actually run it now, right? So we'll just run it as any normal application. And here we start getting our data out. So it'll tell us how many iterations, and then it'll tell us, what we asked for. So the number of bytes transferred, and the speed, so 20 gigabytes per second for the 8K example. Then, so this is going to be, remember we started at 2 to the 13, right? 14, 15, 16, right? And so we're going all the way up to 2 to the 26 over here, right? And so we can see, our different, what we really care about is this number right here. So this is going to be, let's go ahead and zoom in on this. What we really care about is this bandwidth right here. And we see some interesting things here, right? So 8, 16, and 32K end up having all around the same bandwidth. But then once we get to 64K, it ends up going down a decent amount, and then it keeps going down. So we fall off a cliff here, our first cliff, at about 128K, and then down to 256K, keeps going down, 512 keeps going down, right? Not quite as much from 128K. And then we, again, at 1024, we go down until we get down here. Once we start getting to, this 8, down here, this 8192K, right? So, we're all the way down at 3, and past that, we're all the way down at 1, getting to half a megabyte per second, right? So it gets incredibly slow down here. So why do we care about this in terms of, the memory system? Well, it turns out we get some very interesting things here, right? So here's our information on our CPU caches. So we have an L1 data cache that's 32K. We've got an instruction cache. Here's our unified L2 cache that's 256K. And their unified L3 cache that's 8192K. And remember, these are random accesses. So 8K, 16K, and then 32K, they all fit pretty well within our 32K cache. So what ends up happening? They all end up having around the same, we end up keeping the same bandwidth. That's pretty high. But after we go to 64K, we've exceeded the size of our L1 data cache. So, caches aren't perfect. What we're going to do is we're going to start missing. We're going to start missing and having to go to our L2 cache. So we start going down, right? And once we get to 128K, right, we're really starting to thrash that L1 cache, right? But then, right, so we've got an L2 cache size of 256K, right? So, we end up, kind of leveling out a little bit, right, at 256K. What's kind of interesting here is that at 512K, it ends up still having around pretty close to the L2 bandwidth that we had right here, this 12, down to 11, right? So this isn't nearly as steep of a jump as going from 128K to 256K, right? So this will blow out our L1 cache, but it seems like the L2 cache is still pretty good at handling the 512K case. But we see that once we start exceeding it by a lot, right, and we start going to the L3 case, right, so we start dying in our L2 cache now. The L2 cache starts to not work quite as well. We're all the way down at 7, down to 6, down to 4, down to 3, right? And once we get to 3, right, we see that 3 is really starting to 3 things are really starting to get bad, especially once we start exceeding this 8192K, which is the size of our L3 unified cache. And the reason why is because once we start missing in our L3 cache, that means we're going to memory, which is why once you start really blowing out your L3 cache, we're talking about, on the scale of, megabytes per second, once you start having no locality at all. So that's just kind of a really cool thing you can do to really understand how your architecture is working, right? But there's more that we can look at here. And so and if we want to really narrow in on a single example, what we can do is run cache bench, right? But we can set some things. We can do this -- benchmark filter. And let's say we only want to run a single run, right? So let's say if we want to run, we really want to check between 15 and 16. So 15 when we're still hitting fairly well in our L1 cache, and 16 when we start missing in our L1 cache. So we can just say, okay, we'll set this to cache bench 16, or first, right? So cache bench, comma 6 or slash 16, right? Or 15 to start out with the 32K version, and then we'll also set the amount of execution time that we'll run for this. So we'll set benchmark min time is equal to 2 seconds, right? So we'll go ahead and run this, and we'll just get a single output, right? So we'll see that, so here's our 32K, still at 20 gigabytes per second, so fairly stable there. But once we go to past that, right, so once we go to 16, so what happens here? So once we go to here, it's still actually fairly good, right? So it doesn't get that bad. But what happens once we go past 64K, right? So let's go to, say, 17. Let's actually run that again so it's at the top of the screen. Right, so once we get here, right, it really starts dying at 128K when we start dying in our L1 cache, right? And there's some other cool things that we can do here, right? So we can call, say, we can use a Linux tool called perfstat, right? And we can start looking at the performance counters, right? And so here we've got, a number of things, including the number of page faults, the cycles, the instructions, the branches, the branch misses. And depending on the support for your particular architecture, you can get even things like compare cycles to the amount of stalled cycles. You can get percentage of stalled cycles, and you see that it really starts getting bad once you start missing in your caches, right? So the next thing we can do, right, other than perfstat, is we can do a perf record, right? So perf record will generate some information for us. So let's run it this again, right? And this time it'll generate kind of a record for us. So you see we've got this perf data in here, and we go ahead and do perf report. It'll generate a report for us, right? So here we've got our report, right? And we can see we've got cache bench in here, and we can even look at what part of cache bench is causing the most problems, right? And so here's our loop in here, right? And we can see what it's comparing against, right? But we'll talk about this more at another time, where we'll go in depth on how to use perf. But that's going to go ahead and do it for this video. So as a bit of a disclaimer, this this example was taken from C++Con. So I'll link this in the section below, right? So feel free to check this video out. It's a really great video where they go over this example, and they go over this in even more depth. As always, all this code you can find at github.com/coffeebeforearch. So this is in C++ crash course, right? So we can look at this in optimizations, and this is in Google Benchmark. So feel free to download Google Benchmark at Google's repository. I'll go ahead and link that below as well, and feel free to check that out, check this code out. But as always, I'm Nick, and I hope you have a nice day.